Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi again, everyone. Okay, so in this video, I will talk about new topic related to the control systems, which is the reduction of multiple subsystems. So this chapter is chapter 5 in the textbook. Okay, for nice third edition, the old version. But nevertheless, it's in a different chapter for the new text, for the new edition. So in this topic, we will learn important definitions of block diagrams and signal flow graph, signal system, summing junction, pickup point, series, cascade, and feedback forms. And this is the main discussion, which is how to simplify block diagrams. Okay, and we will look at some examples. So for this course, we will not look at signal flow graph, although you are free to study it on your own. Signal flow graphs is just another way of representing block diagrams using lines and dots and arrows. Okay, so we will focus our attention to block diagrams. Right, we have been working with individual subsystems represented by a block with its input and output. However, more complicated systems are represented by interconnection of many subsystems, and we want to represent multiple subsystems as a single transfer function. This is always the problem that we look at before. Okay, we have a physical system. We represent them using mathematical equations and then block diagrams. And then sometimes you combine several subsystems together, causing you to look at the overall system to be quite extensive. So how can we simplify the overall control systems into one simple transfer functions? Okay, so we will focus our attention to the block diagram here. Okay. So first of all, let's look at the different components of a block diagram again. So as before, you have seen how we can represent signals using arrows. Okay, so we label, we use an arrow and we use alphabets to represent different signals. So R normally the reference signal or the input, and C is the output, or the normally the control variable. And then we have a block diagram representing a system, okay, relating the input and output for a particular physical model, for a particular physical system. And then we could have a summing junction, okay, represented by this symbol, okay, where we may have several signal going into the summing junction together, and the output is just the summation of the signals going into the junction. So in this case, you can see the inputs are R1, R2, and R3, and then the output is C equals to R1 plus R2 minus R3. So you can see the sign going into the summing junction will indicate whether it's going to be added or subtract, okay, from the overall output signal, to make the overall output signal. And finally, pickoff point. So normally we would indicate it here. Let me just, okay. So pickoff point is this point, okay, where the signals are separated. Okay, so this is just a different way of just showing the same signal, okay, separated into different arrows. Probably fed in the signals will be fed into different subsystems. Okay, let's look at the first form. Form means a typical a typical structure, okay, for a block diagram. So the first form we will be looking at is the cascade form. So in this case, you have two subsystems, G1, G2, and G3. They are connected in what we call in series, okay? And so if it's in series, so we call it in cascade form. So you have the input and you have the output C here. So you have input R. So in this case, the output of the first block x2 is equals to just G1 times R. Okay, this is G1, so this is R, so the output is G1 times R. So now this G1 times R will be going into the second block, hence the output of the second block will be G1 times R times G2. Okay, G1, G2, and R. Now this same signal is fed into the third block G3, so the output will be this signal G2 G1R times G3, so hence you will get the overall output. So as you can see that it's equivalent to, so if the overall input the input is R and output is C, then the overall signal will be just G3 G2 G1, so it's equivalent. The equivalent signal will be just as shown here, where it's just C is like you are multiplying all these blocks G1, G2, and G3 together. So it's equivalent for you to just draw one block instead of three blocks. Yeah, and inside the new block will be G1, G2, and G3. So you just multiply the transfer function together, okay, if it's connected in series, or as we call it in cascade form. So that's very simple. So as you can see, this is the equivalent transfer function. However, there is a note here that the equation above was derived under assumption that interconnected subsystems do not load adjacent subsystem. So that is, the subsystem's output remains the same whether or not the subsequent subsystem is connected. So consider the network below. So as an example, if we are using we are looking at electrical systems. So if we have first system G1, so this is an exception to the rule here, okay, an exception where loading occurs. So if the first subsystem does not load, okay, i.e. the output does not interfere with the input or the circuit or the model of the second system, then we can do that. However, this is an exception. So if you can see here, if you have a first circuit G1, if you have the transfer function for the first circuit is V1, this is V1 minus V1 over Vi, this is Vi, okay, this is V1. So if G1 is the transfer function, and if you have a second circuit, G2 is the relating the output V2 and V1, okay. So if you connect this circuit together, forming this third circuit, okay, if this is the resulting circuit, then you will see that the cascade rule will not apply here, okay, because if you connect these two circuits together, then loading will occur. So the first circuit will load the second one, and has the output V2 over Vi does not equals to this G1 times G2, okay, this is G1 times G2. So although you connect the circuit in series or in cascade form, but in the sense of a block diagram, it doesn't happen, okay, as a series multiplication. However, typically in modeling of circuits, you can add a voltage follower. So this is an amplifier, voltage follower. I think you learned that in electrical circuits. So if you just add a voltage follower, and if the gain is 1, K is equals to 1, then you can apply GT, the overall transfer function, equals to V2 over Vi equals to KG2 times G1. So if you use voltage follower with gain 1, then definitely the output or the equivalent block diagram will just be the multiplication of G2 and G1. Alright? Okay, okay, that's the cascade form. Next is the parallel form. So in the parallel form, so we have a signal R, and it is going through 3 different block diagrams as an example in this case. So you have X1, X2, and X3. So RG1, RG2, RG3. So all of the signals are fed into a summing junction, and hence the output is equals to whatever the signal going into the summing junction. So you just add all the whether it's plus or minus, and the equivalent signal is just plus or minus G1, G2, and G3. Okay, so this is parallel form. So in cascade, you multiply the block diagram together. In parallel form, you add or subtract the block diagrams, i.e. the transfer functions representing the block diagrams together. Okay, so again, cascade, you multiply, as in this case, multiply if it's in series. In parallel, you add the block diagrams together. Okay, that's the two most basic form. And the third one will be the feedback form. Okay, we have seen this signal before, the signal, the feedback form as shown here. So you have the input, so assuming the controller and plant, and then the output of the controller and plant is fed back through a sensor normally into a summing junction. Okay, indicated here minus plus. So if you write down the equations, E, okay, the output of the summing junction, E equals to R, and then C, E is equals to R plus minus H2 H1C, or in this case we simplify it further as a simple, so we combine the sensors, the plant and controller together in this case, right? So if we have R, E, C, so we have 3 signals here. So we have R, C, and we label the output going out of the summing junction as E, which is the error. And we have the plant and the controller G and H. So if you write down the equations, okay, C is equals to E times G, and E is equals to R minus plus HC. Okay, so you have 3 unknowns, you have 2 equations. You can write one, you can represent E in terms of R and C, and you write, you eliminate E, you will get that C is equals to G over 1 plus minus GHR. So this is the feedback form. Okay, you can write the equations. You can verify that easily. Okay, so if we have a feedback form, then the output will just be the G, okay, the forward path, G over 1 plus minus, depending on the sign. If you have negative feedback, then it's positive here. If you have positive feedback, then the sign is negative in the denominator. Okay, so that's simply how you memorize that. You can verify that later using equations. So C is equals to G over 1 plus minus GH if you have a feedback form. So so again, let me summarize now. 3 basic forms: the cascade, the parallel, and the feedback form. So these 3 main components will be used to simplify more complicated block diagrams. Okay, so the idea of simplifying block diagrams is we move blocks to create familiar forms. The familiar forms are, as explained before, which is the 3 types, which is the cascade, parallel, and feedback. So assuming we have a situation here, okay, let's just look at the situation. Sometimes there is a necessity for you to move this G where from its original location. In this case, the original location is after the summing junction. We want to somehow move it before the summing junction. Okay, why? There must be some reason, because when you do that, probably you will see that there will be a familiar form in the to the left of the summing junction, and then allows you to simplify the block diagrams. So if you move it before from this original location G, which is after the summing junction, and you want to move it before the summing junction, then what you need to do is, this is a parallel form, so if you move it, then you have to add the block in both signal going into the summing junction. So this G, there was originally no blocks here, but because you move it before the summing junction, then you have to add them physically. Okay, this is one situation. So the next one is if you want to move a block to the right past a summing junction. So look at this situation carefully. So in this case, we have a situation where we have to move a block to the right past a summing junction. So in the original structure here, you have a summing junction and you have a signal R going into the summing junction, and you have a signal X going into the summing junction, and this output is C. Alright, so C is equals to RG minus plus X. So as you can see, you want somehow to move this block past this junction, okay, for some reason, right? So for some reason you want to move this block past this summing junction. So what happens is, if you move this, so originally you have G here, and if you move it to the output, then you can remove the G here. Alright, and now the G is after the signal, okay, here. But as you can see, originally this signal, it does not have G here. So in order to ensure the equivalence of the original system here, right, you must add 1 over G here, because originally there's no G here, right? So you move G outside here. So originally X just goes into the summing junction. So because now this signal X somehow will be multiplied by G later on after the summing junction. So you have to add a block 1 over G to ensure the equivalence of the original system. Okay, so that's how you move a block before to after the summing junction. So if originally the block is there, you just, when you move it, so you remove the original block here. But all the signals that does not have G, you have to multiply, you have to create another block, which is 1 over G. Okay, that's how you do that. Next, pickoff point. So here you have the pickoff point here, right? So now if you want to move this G from, so we can say G is now located after the pickoff point here. So if you want to move this G to before the pickoff point, then you can do that. So as you can see, what happens now when you move that, so the G block here now becomes it's located to be before the pickoff point, right? But now what happens is, for the other signal going out of the pickoff point, you now have to add 1 over G here to ensure that the signal remains the same. So you can check later. This is still RG. This is so if you write down the signal, it's RG going here. and this one G times 1 over G is still R, and then same thing with this, right? That's going from after the pickoff point to before the pickoff point. Next is what happens if you want to move this block to from before the pickoff point to after the pickoff point. So this is what's going to happen. So then G will be, you have to, from originally here, you want to move after the pickoff point. Then what happens is you have to add the blocks into all the pickoff point. Okay, so again, this is the pickoff point. Okay, we're talking about the when we say pickoff point, this is what we mean. Okay, this is in the red, that's what pickoff points are. So before, so if you want to move after the pickoff point to before, this is what you do. Okay, if originally the signal here, there's no pickoff point, so then you need to add a block there. Whereas in this case, if originally is this RG, you want to move after the pickoff point, then you have to add these blocks into all the signals going out of the pickoff point. Right? So let's look at example. So again, what I have shown you so far are the basic structures. We call it the familiar forms. Okay, the familiar forms consist of the cascade, the series one, and then the parallel one. Okay, this is the series. Okay, assuming there's no loading effect. So we have the series, and then we have the parallel. Okay, which is this one, and finally we have the feedback form. Okay, and then I've shown you simply how to move blocks from after to before summing junction, vice versa, and also from and after pickoff point. So make sure you know this rule, then you can use that to simplify complicated block diagrams such as this one. So let's look at an example. So we need to find the transfer function relating C and R. So you can see there are several existing forms already here. So how do we solve this problem? Okay, so first of all, you can see, okay, this one. Okay, so assuming there's no loading, so we can say that's the series connection, so the cascade connection. So then you just multiply the blocks together, and then when you have a signal going into a summing junction such as this one, then you know the output. So this signal going into the summing junction can be added together. These are the parallel forms. Okay, so this part are now the parallel forms, and all you need to do is you can just this is the parallel form, so this part you can add them together. So you can see H1 minus H2 plus H3, and finally this part is the feedback form. Okay, which is the output will just be the forward path over 1 plus the forward times the feedback path times G1, excuse me. Okay, so you would have the overall transfer function as shown here. Okay, so there is combination of cascade, parallel, and then feedback, and then another cascade. Okay, so this is the feedback. Okay, this is the feedback multiplied by another series, which is the G1. Okay, so please check that. Next, another example. Okay, so you can see again this example available in the textbook. Okay, so in this example you can see the parallel and feedback form are not really especially in this part of the block diagram, it's not really clear whether you have parallel, cascade, or feedback form. The feedback and the cascade and the series form is not really clear initially, right? Although you can see here, as I've outlined in the blue circle, that's you can see that there's actually a feedback form inside, okay? And then the rest, it looks not obvious, okay? It doesn't look obvious, okay? So that's why this requires practice. You can see, let's look at the one in red here. There's a pickoff point. The idea is we want to move this block, okay, from after the pickoff point to before the pickoff point, to see whether we can have a easier system to work with, right? So in this case, if you move this G2 from after the pickoff point to before the pickoff point, then you will see we will do that. G2, that's V4, and then you need to add another block 1 over G2 here. Okay, initially in this path, along this path, there's no G2, there's no block, there are no blocks in that particular path. So if we want to move this G2 after this pickoff point, then it becomes that way. Okay, so we move it from here to here. So what happens is, okay, nothing happens here, but here you have to add 1 over G2, right? And then this blue circle is actually a feedback form, so you can just apply the feedback form already. It's just G3 over 1 plus G3H3. Okay, so now let's look at what happens now next once we have moved G2 there. So you can see here, this is a parallel form, right? Once you have done that, this becomes a parallel form. So now I have highlighted in blue. So now let's look at this another structure G1, G1 and V3 here. Okay, so we can see here that yeah, so in this case, if we want to, we can see another feedback form here. This is parallel, so this one is easy, 1 over G2, so it's just 1 over G2. This is 1 here, right? That's just 1. Okay, let me just, so that's 1. Okay, this is 1 over G2, this is 1, so then you have 1 over G2 plus 1. Okay, that's parallel form, that's easy. Okay, but over here, what we're going to do is we're going to move G1 from here before the summing junction to outside. Okay, so what happens then, if you move a block from before to after the summing junction, so initially, so all you need to do is you put G1 here, and then here you need to have 1 over G1, because originally G1 is not here. So all you need to do is you add 1 over G1. So what happens is G1, G2, H2 over G1. Okay, that's what happens. So next, so this is another parallel form, H2, G1 and H1. So this is H2 over G1 plus H1. Okay, yeah, these two can be combined together. The blue one is just the cascade form, and then you have combined this into parallel form, and then from here you can see it's a feedback form. Okay, so you apply the feedback form using the feedback formula, and finally you would have the cascade form again. Alright, so that's how you simplify block diagrams, by identifying a block, moving it from original location, whether before or after summing junction, and find a block whether you want to move it from before or after a pickoff point. Okay, so this requires practice. Depending on the situation, you apply it accordingly. Okay, finally, if that doesn't work, in some cases, sometimes it's not obvious to find the fundamental blocks, cascade, parallel, or feedback within a particular block diagram. Sometimes you can just use equations. So analyze only the difficult section of the block diagram using equations. So first, you need to identify the signals coming out of summing junction. So that's the location where the complication occurs normally. And then make sure that there are no other signals except the input and output signals. Okay, and then find the total number of signals within this section. So assuming you have n signals, and then you find n minus 1 equations that relates the n signals. And then you solve the equations to obtain the transfer function for this part of the block diagram. So I'll illustrate this part of the notes using one example. So this is kind of difficult example where it is not obvious where you want to move the blocks. Sometimes even if you move some blocks, like for example here, you want to move it here, it doesn't really show the whether it's parallel, feedback, or the cascade form. Okay, so it's not, and then you have a split here, so it looks very difficult in this case if you want to apply the um, previous rule in this kind of example. So find the transfer function relating output K and input M in terms of system parameters using block diagram reduction technique. So the last one here, okay, you can see there's this part. I think is kind of difficult to see what to do, right? In this part. So this is where sometimes you can just use equations to solve the problem. So like I said in the rule, identify the signals coming out of summing junction. So say you can see if you can solve for this part of the, okay, if you can solve for this complicated part of the block diagram, then you can see this is just series, this is feedback, the other one is also another feedback, but this one is not clear. Okay, so like I mentioned, what you can do is you identify signals going out of a summing junction. So you have 1, 2, 3 summing junction here, so you can label all the signals together, and then that will be the input of that signal. You have 3 signals, so you just need to identify 2 equations to solve the problem. So for example, in this case, summing junctions are A, B, and C. So let's just label them A, B, and C. So you can label another signal R, okay, going into the red block. Okay, so this R is going into the red block, which we want to simplify. So if we can solve for R and C, then you can solve for the overall block diagram. So again, 3 summing junction. So we have labeled all the signals going out of summing junction, which are 3. So then we need 2 equations. That's all. Okay. Okay, as indicated here, we have, sorry, so in this case we have label 4 signals actually, so there's another one R here. Okay, so we want to simplify the blocks relating R and C, but we have identified all the outputs going out of the summing junction A, B, and C. So then we have 4 signals, so we just need to find 3 equations, right? Just like what the notes say here, right? So we have 4, so we need 3. So in our case, this is 4, right? Sorry, so we have in our case 4 signals in our case. So then 4 minus 1 is 3, so 3 equations. So you can see it's not that difficult to write the equations. If you write A equals to G2R, right? G2 times R minus H1 times C, right? A is equals to G2R minus H1 times C, and then B is equals to R times G3 minus H1C, and finally C is just AG4, right? Just look at this signal, A times G4, B times G5. Okay, now you can eliminate A and B easily from these three equations. Okay, you can see that C is equals to G4 if you substitute A here, and then B into here. Okay, B, this is, okay, A you substitute here, B you substitute here, so you have the relationship between C and R, and you will see if you solve that. So G2R minus H1C, this is A. Okay, let me just clear that out for you. So that's A, this part is A, and this part is B, right? And then you can solve for C. So you can group C. You can find the expression for C and R, right? Okay, you have to substitute. You have to find the multiplier for C and R, and you can solve for C and R to be this transfer function. So now the block diagram is just C over R is here, PS. So now you can see you have a cascade form, you have a feedback form, two feedback form. Okay, so you can easily spot the fundamental blocks, solve using block diagram reduction technique. So now you can just do it easily. Okay, because you have solved the complicated inner part of this. You can try to solve using by moving the block past the pickoff point or past the summing junction. You can move it around. You can try, but you will find it's kind of difficult to do that in this kind of situation. But it's up to you. Okay, there are so many ways to do that. So you can also use equation. The equation is you identify the output or the signal going out of summing junctions in that particular block diagrams, and then you write all the signals together, find the n-1 equations. Okay, so that's it for this topic, a very short topic on how to simplify multiple subsystems. So although we didn't use signal flow graph, there's another way to solve it, but it's not included for this course, right? So again, let me remind you, there are three different familiar forms. There's the cascade, parallel, and the feedback. So you can write down the formula for that. And then how to move blocks past or before summing junction, and how to move blocks past and before a pickoff point. And then you will apply the familiar forms rule. Okay, or otherwise, if it still doesn't work, you can just write down the equation for a small part of the block diagrams to allow you to solve the overall problem. So that's all for this recording. Thank you everyone for your attention. We will meet in whether physical or online class, just to clarify any questions if you have regarding this topic. So thank you everyone. See you next time. Bye bye. Assalamualaikum warahmatullahi wabarakatuh.